now my
Hello.
phone. Yeah, okay. So, yeah, my phone disappeared. So, anyway, it's a great pleasure to welcome Manjil Saikia from Cardiff University, and he is going to speak on refined enumeration of symmetry classes of alternating sign matrices. And we hope to see at least one formula, some complicated formula from his work.
So thank you so much, Gaurav, for the invitation, and it's very nice to be here and give a talk. So I have been to the seminar a couple of times, and it's very nice. So thank you so much. First of all, I would like to apologize that this is not very connected with the themes of special functions and number theory. So this will be mostly combinatorics, but there are a few formulas which involves rising factorials and binomial coefficients. So this is part of this is I mean mostly this is joint work with Ilse Fischer, and there will be a few more results, new results at the end. And this was done last year during my PhD, and the paper is available online in the archive, and the title is the same as the title of this talk. So let's begin with this sequence 1, 2, 7, 42, and so on. The sequence is given by the following nice formula. So you see that this is a quotient of product of factorials. And for me, nice formulas would be something like this, or sums over formulas of this type. Also nice in this sense is that if you do the prime factorization of these sequence, then you will see that the prime factors are usually small. And yeah, so in some sense that would also be nice for me. So if the prime factors are small. Or in more compact product notation, we have this. So this formula was conjectured by Mills, Robbins, and Ramsey in the early 1980s. And they conjectured that this formula counted newly introduced objects called alternating sign matrices. So this will be the focus of my talk, these objects, alternating sign matrices. And let me define them. So an alternating sign matrix of size n or order n is a square matrix, n times n square matrix, with entries in the set 0, 1, and -1, with the following conditions. The first is that all row and column sums are equal to 1. And the second condition is that the non-zero entries, they alternate in each row and column. So clearly all permutation matrices are alternating sign matrices because they have entries in the set 0 and 1, and all row and column sums are equal to 1. And since there are no negative ones, so the second condition is satisfied anyway, because there is only one in each row and each column. So for instance, there are 7 alternating sign matrices of order 3. These are the 6 permutation matrices, and the 7th matrix is something like this. So this has a -1 in the middle. And if you look at the sum of each row and each column, then you will see that it sums up to 1. And if you look at this row, you see that the non-zero entries, they alternate in sign. So after a 1, there will be a -1, and then 1, and so on. So there can be zeros in between, but the sign has to alternate. So as I mentioned already, that the formula was conjectured by Mills, Robbins, and Ramsey, and this conjecture was proven by Doron Zeilberger and independently by Greg Kuperberg, and they used different techniques to do this. So in fact, Zeilberger proved a stronger statement using something called constant term identities, and Kuperberg, he exploited some connection with statistical mechanics, statistical physics. So if there is time, I'll explain a bit about Kuperberg's proof. Otherwise, I'll not go into details about this. So let's see how they were first defined. I mean, how did the Mills, Robbins, and Ramsey came about these matrices? So we use the notation Aij to denote the matrix A, to denote the matrix that remains when we remove the ith row and the jth column from a matrix A. And if we are removing more than one column or one row, we just add. So if you're removing 2 rows, then we just add 2 indices in the superscript. And if you're removing more than one column, then we add the indices in the subscript. Then a famous theorem is by Denanio and Jacobi. It's called the adjoint matrix theorem, which says that given a matrix n cross n matrix, then the determinant of this matrix can be written in terms of determinants of smaller matrices. So this observation is crucial, that you can have the determinant of these bigger matrices in terms of smaller matrices. So you see that all of the matrices which appear on the right hand side are now n minus 1 times n minus 1 matrices, and this matrix is now a n minus 2 times n minus 2 matrix. So you can also write this in this more compact way. So this gives us a way of evaluating determinants in terms of smaller determinants. So of course this has to be non-zero, but yeah, okay. So this was the basis by which we can have an algorithmic way of doing determinants in terms of 2 times 2 determinants. So for instance, we have this 3 times 3 matrix, the determinant of this matrix using the previous theorem. We can write it in this way. So if we remove 2 rows, the first and the last 2 columns, the first and the last column and the first and the last row, we are just left with these entry. And the determinant of a single entry is just that entry itself. So 1 divided by this entry. And then you have this smaller 2 times 2 determinant. So in this case, I'm removing the first column and the first row and so on. Here, I'm removing the first row and the first column, the last row and the last column. And here I'm removing the first and last row and columns alternatively. So you see that these smaller matrices are now 2 times 2 matrices. And once you evaluate all these determinants, then this also becomes a 2 times 2 matrix. And the determinant of this bigger matrix now is written in terms of all smaller submatrices, which are basically 2 times 2. So we can generalize this. So I don't have the slide, but you can do this for 4 times 4 matrix as well. So to do the determinant of a 4 times 4 matrix, you write it in terms of determinants of 3 times 3 matrices, and then using these this observation in this slide, you just write the determinant of 3 times 3 matrix in terms of 2 times 2 matrices. So so in 1980s, Robbins and Ramsey, they looked at the generalization of this algorithm, this sort of calculation. So what they defined was something called a lambda determinant. And the definition is the following. So the lambda determinant of a 2 times 2 matrix is now just the product of these 2 entries plus lambda times the product of these 2 entries. So you see that if lambda is equal to -1, then you just get the normal determinant back. And using the previous observation where you were generalizing these bigger determinants in terms of smaller ones, you can do the same thing for this. And you get a generalized lambda determinant for n cross n matrices as well. So what Robbins and Ramsey, they proved was that the lambda determinant of this matrix, of a square matrix A, is now the sum here is given by this formula, and the sum runs over alternating sign matrices. So here script n is the set of all alternating sign matrices, and the IB which appears here is the inversion number of these alternating sign matrix, and NB is now the number of -1s in the alternating sign matrix. So this was the formula that they found, and they naturally wanted to evaluate how many alternating sign matrices of a particular order are there. And they did some computer experiments, and then they conjectured the formula that I showed in the first slide. So this was the first appearance of an alternating sign matrix in the literature. I mean, it appeared earlier, but I think this was the first work. So you see that the date is 1986, but yeah, okay. So very quickly, what is an inversion number of an alternating sign matrix? So here we have a 5 times 5 alternating sign matrix. So you see that there are 2 -1s. An easy way to, so there is a formula which you can write down in terms of the entries of these alternating sign matrices for the inversion number. But an easy way to look at this is to take products of all pairs of entries for which one of them lies to the right and above the other. And then you just add them up. So if you do this technique here, then you will see that there are 7 pairs whose product is +1. and two pairs whose product is -1. And then you just add them up. So this will be 7 minus 1, 7 minus 2, and the inversion number would be 5 in this case. So this is not important for the rest of the talk, but just to be self-contained, I just mentioned this. Okay, so how does one get a formula for this? So let us have some observations. So this will be important for the rest of the talk. The first observation is that we can have only one non-zero entry that will be a positive one in the top row. And because of the inherent symmetry of the square, so if you have something fixed for the top row, then you can also say that you will have a single one in the first column, the last column, and the last row as well. So how to see this? So suppose you had a -1 in the top row. So suppose there is a -1 which appears in the top row, and you suppose the -1 appears here. Then you look from the top of this column where the -1 appears, and then you look at the partial sums that you can do for this column. So since this is there is a -1, then the next non-zero entry has to be a 1. So the partial sum up to that point will be 0. And after that 1, the next non-zero entry has to be a -1 because of the alternating condition that we have. So the partial sum would be -1 in that case. So you see that however way you do this, the partial sums would always be 0 or -1. It cannot be 1. So the column sum cannot be 1. So that is why there cannot be a -1 in the first row. And as I said, because of the symmetry of the square, so you cannot have this in the first column, the last column, and the last row as well. So this is the crucial observation that there is only one non-zero entry in the last row, and the first and the last column, and that non-zero entry has to be 1. So if we denote A sub nk to be the number of this order n alternating sign matrices with a 1 at the top of the kth column. So suppose, for example, this would be something which is counted by A 4 3. So n will be the order, and k would be the position of the 1 in the first row. So this will be 3 here. So we denote by A and k to be this quantity. So if you think about this for a moment, then you will see that there is a symmetry. So A n k is equal to now A n plus 1 minus k. You just flip this matrix, and you will get this symmetry. Flip it along the vertical axis. And if the 1 appears in the corner, that is the position of the 1 is in the first column, then all of these will be zeros, because there cannot be a non-zero entry. There cannot be two non-zero entries in the first column. And similarly, all of these will be zeros. So whatever you have here would again be an alternating sign matrix, but now of 1 degree smaller. So 1 order smaller alternating sign matrix. So this is written here. So A sub n1 is now just A n minus 1. So the number of alternating sign matrices with the one fixed in the first column, first position, is just the number of alternating sign matrices of 1 order less. So this allows one to check small values, and you can get some sort of a guessed formula. And Mills, Robbins, and Ramsey, they did that. And they first conjectured that the successive ratios, so A n k divided by A n k plus 1 is now a nice rational function in terms of k and n. And once you have this conjecture, then it's not, I mean, it's okay. So you have some steps, but you can just, yeah, so, okay, I mentioned the steps as well. So what you can do is the following. So A n1 is now just summing over A n minus 1 k, because the number of all alternating sign matrices, if I denote by an, is just now sum over all the possible, all the number of alternating sign matrices with the possible positions at the kth place. So you sum over all k's. So you take k equal to 1, 2, 3, and so on. And if you sum over that, then you just get an. So this is basically what is written here, but I write this for an minus 1. So you can notice from here that these a and k's are uniquely determined by the a and k minus 1s. And from here, using this summation, you can write down the formula. So the conjecture that I showed you in the last slide can be reformulated in terms of this binomial coefficients, and then you have this product. So if you remember from the first slide, I mean, it's difficult, but if you remember, you'll see that this is just the number of n-1 order alternating sign matrices. So the formula was an was just this product, but instead of n-2, we had n-1. Anyway, so from here, knowing that an equal to an plus 1, 1 allows one to conjecture the ASM enumeration. So you just put k equal to 1, and n you put n plus 1, and then you can get an. Okay, so this was some sort of historical remark. Let's look at some other objects which are counted by the same sequence. So this sequence appears in multiple contexts in combinatorics. One of these contexts was the alternating sign matrices, which I explained. But let's look at a few more objects. I think I have 2 or 3 in the slides. So this combines several results. So the following combinatorial objects are counted by this formula. So I already showed you that I already showed you what are alternating sign matrices, and this was conjectured by Mills, Robbins, and Ramsey, and proved by Zeilberger. So this also counts a certain class of descending plane partitions. So these are objects which were introduced by Andrews, and you'll see that it appeared before than alternating sign matrices. And Andrews did not. Andrews proved that a particular class of all descending plane partitions is counted by this formula, but it took some time to realize that alternating sign matrices and descending plane partitions are counted by the same formula. So the story is very nice, and it's available in a book by Bressoud, which I'll mention later on. The third class is something called totally symmetric self-complementary plane partitions. So I think I have an explanation for this later on. And a very recent class is called alternating sign triangles. So this was found quite recently by Erwin Dyer, who is in the call, Roger Behrend, and Ilse Fischer. And I have a slide which explains what these are. So these are, as the name suggests, that these are some sort of triangular arrays similar to matrices. The conditions are very similar, and these objects are also counted by the same formula. And there are a couple more, but I don't mention this. Okay, so one of the major open problems in enumerative combinatorics is to find bijections between the objects that I mentioned in the previous slide. Recently, Fischer and Convalinga, they have given a bijective proof of the DPP-ASM part, but it's a complicated bijection. So this paper contains a very nice overview of this bijection, which was published recently in September, I think. Anyway, so does the story end here? So probably not, because I still have a lot of slides left. In the late 1980s, Richard Stanley, he suggested the study of various symmetry classes. So since you have a square, so the dihedral group acts on it naturally, and then you have several symmetry classes. And you could ask similar questions for these symmetry classes. Like how many of a particular symmetry class exist, and so on. So this led Robbins to conjecture formulas for many of these classes. And I did not mention this before, but the proof of the alternating sign matrix conjecture, which was done by Zeilberger, is complicated. So it was considered to be a hard problem, and even the enumeration of these symmetric classes turned out to be difficult. And this was only completed recently in 2016 by Matthias Convalinga, Roger Behrend, and Ilse Fischer. So let me just mention all of the symmetry classes that we can have. So we can have a vertically symmetric alternating sign matrix. And this was enumerated by Greg Kuperberg. So you'll see that Kuperberg's name appears several times. This was done in a very famous Annals paper in 2002. So he did several of these symmetric classes and much more in paper. So the second class would be half-turn symmetric alternating sign matrices, so which are ASMs invariant under a rotation of 180 degree. Then you can have diagonally symmetric ASM, sorry, the half-turn symmetric ASM has two different formulas for odd and even case, and this was done by Kuperberg for the even case and Razumov and Stroganov for the odd case. Then you can have something called diagonally symmetric ASM. So there is no nice formula in the sense that I mentioned in the first slide, where it's written in terms of quotients of factorials or products of factorials or sum over such quotients and products. But there is a formula which exists now, which is due to Christoph Kuchan, Ilse Fischer, and Roger Barron. So Christoph Kuchan has some slides about this. If you are interested, you can look up in his website. He has a Pfaffian determinant formula, Pfaffian formula for the number of diagonally symmetric alternating sign matrices. The fourth class would be ASMs which are invariant under 90-degree rotation. So these are called quarter-turn symmetric ASM. And again, this was done by Kuperberg for the even case and Razumov and Stroganov for the odd case. Then one can have horizontally and vertically symmetric ASM, and this was done by Okada. Then the final class would be diagonally and anti-diagonally symmetric ASM, which was done recently, as I mentioned in the last slide. So one can also have something called all symmetries, but again, there is no nice formula. So recently, I think there was a paper about this on the archive. I forget, but the formula is again complicated, so it's not a product formula. So anyway, so these are some classes that we'll be looking at. So not all of them we'll look at. I think we'll look at only vertically symmetric and horizontally symmetric case, and later on quarter-turn symmetric alternating sign matrices as well. So this is somehow midpoint of the talk, and if you have any questions, then I can spend some time answering about the definitions and whatever I have mentioned so far. So I cannot see this chat or anything, but Gaurav, if there are any questions, then I'd be happy to take at this point.
Yeah, it doesn't look like there are any questions so far.
Okay. Okay, so let's go into the refined enumeration of ASMs. So I already mentioned this first observation. So here I have a bigger ASM, which is now a 7 times 7 ASM. So I have already mentioned that there is only one in the boundary row and column of an ASM. Okay. So this suggests, already I have mentioned that this suggests how many, we can ask the question that how many ASMs with the position of the one fixed at a certain row and column, at a certain boundary row and column exists. And I already showed you a formula for this for the alternating sign matrix case, the unrestricted alternating sign matrix case. And these kind of formulas are called refined enumeration of ASMs. So this was the formula which I showed you in one of the previous slides. This was conjectured by Robbins, and this was proved by Zeilberger after he proved the alternating sign matrix conjecture. So for this, he used the techniques of Kuperberg, and he did this shortly after Kuperberg's paper appeared. So several people have worked on refined enumeration of ASMs. This is a typo, and as well as refined enumeration for the symmetry classes. So some of these people are mentioned here. Roger Barron, Ilse Fischer, Dan Romick, Razumov, Stroganov, Arvind, Dan Romick with his student, and so on. So I want to show you some X conjectures which we were able to prove, Ilse and me. So the first was a conjecture by Ilse, who conjectured a formula for the number of vertically symmetric alternating sign matrices. So the first, the letters before ASM in such an acronym would signify the symmetry class. So S would always be symmetry, and then V, VS, H, and so on. So if I have V, it will be vertically, and if I have Q, then it will be quarter turn, and so on. So Ilse Fischer had a conjecture for the number of vertically symmetric ASMs with the position of the one in the second row. So I'll explain why the second row and not the first row in the next slide. Then Robbins had some conjectured formulas for quarter-turn symmetric ASMs. So these were not very difficult. Duchon also had something for quasi-quarter-turn symmetric ASMs, which is similar to the formula for Robbins. So we proved these conjectures, and some more results in recent joint work with Ilse Fischer, and I have some more in refined enumeration results, which is in progress. I have not written it up, but I can show one or two results later on about this. So let's go for the vertically symmetric alternating sign matrix case. So the first observation is that they exist for odd order only. So why is this the case? So if they would exist for an even order, then the vertical symmetry axis would be in between two columns. So suppose this is a even order vertically symmetric ASM, then the vertical symmetry axis would be between two columns. Let us say that these two columns. So we have the vertical symmetry axis here. Then all of the entries that appear to the left of this vertical symmetry axis are the same as that appears to the right of this vertically symmetric axis, vertical symmetry axis. So that means the sum of the entries in the row would now be 2 times the sum of the entries that appears to the left or the right. And that means the sum of the entries would be now divisible by 2. So this is not possible because the sum of the entries in each row and column has to be 1. So that is why vertically symmetric alternating sign matrices cannot occur for even order. So they can only occur for odd order. And once you have this, then the second observation is clear because of the symmetry. So since you have a vertical symmetry, so everything to the left and to the right of the vertical symmetry has to be same. And I said that, and the first condition for the alternating sign matrix is that the sum of the entries has to be 1. So the only possibility, since we know already that the first row has only one non-zero entry and that has to be 1, so the only possibility is that the 1 has to appear in the middle, in the column which is the vertical symmetry axis. Okay. So that is why the 1 is fixed in the first row for a vertically symmetric alternating sign matrix in the middle column. So once you have this fixed one, then the next, if we go to the next row, then again, it is not difficult to see that the next entry below the 1 has to be a -1. So it cannot be anything else. So again, the reason is simple. So whatever entry is here, again, you see that the sum of the entries to the left and to the right has to be the same. And you cannot have a 1 directly below the 1 because then the alternating sign condition will be violated. So the only possibility after 1 are 0 and -1. So if you put a 0, then you cannot put a -1 to the left or to the right, because if you put a -1, again, if you look, suppose this is not a 1 but a -1. So if you look from the top again of this column, then you cannot sum this column up to 1. So this was the explanation for the first observation. So you can have a similar thing here. So if you put a -1 to the left or to the right, you cannot sum that column where the -1 appears to a 1. So the only possibility is that this has to be a -1, and then there has to be 2 1s which are arranged vertically symmetric to the left and to the right. So symmetric with respect to this -1. And we can keep on doing this. If we keep on doing this, we can see that the middle column will always be alternating 1 -1, 1 -1, and so on for a vertically symmetric alternating sign matrix. So it makes no sense to ask the question that how many alternating sign matrices exist, how many vertically symmetric alternating sign matrices exist where the position of the 1 in the first row is fixed, because all of the vertically symmetric alternating sign matrix has this 1 here. So it's not a meaningful question to ask. But you can ask a similar question for the second row, because in the second row you have 2 1s which appears and they are arranged symmetrically with respect to this middle -1. So you could ask a similar question for the second row, namely, how many vertically symmetric alternating sign matrix exist such that the position of the first one in the second row is fixed at some particular column. Here, this is fixed in the second row, second column. So this would be something, this would be a refined enumeration question for vertically symmetric alternating sign matrix. And let me also mention that for the column, this is different, because in the column you can have, in the first column or the last column, you can have a 1. because there is no restriction on this. So of course you cannot have a 1 in the first position and the last position, but apart from that you can have a 1 in any of these positions. And this would be a refined enumeration question for the column refinement in terms of in case of the vertically symmetric alternate sign matrix. And this was already done by Razumov and Stroganov, who proved that the number of a odd order, so order 2n plus 1 alternating sign matrix, which is vertically symmetric, and the position of the 1 is fixed in the ith row. So the position of the 1 in the first column, if it is fixed in ith row, then this number is given by this formula. So Fischer conjectured sort of a similar formula for the refined enumeration of vertically symmetric alternating sign matrices, where the first one in the second row is now fixed in the ith column. And she conjectured that this is equal to this product. You can see that this particular product in the braces is the same as this one. And the 2 and minus 1 is also here. So we were able to prove this formula, namely that the number of 2n plus 1 order vertically symmetric ASM with a 1 in the ith position in the second row is given by this formula, which was conjectured by Fischer. And so I already mentioned that this appears already here. So if you do this, if you sum the formula of Razumov and Stroganov for I and I plus 1, then you get back this formula by conjectured by Fischer. So our proofs are not we exploit some connection with something called 6-vertex model, which I'll explain if there is time. So our proofs are not very combinatorial. A bijective proof of this type of result would be of great interest, and it's not very clear how to do this. So I mentioned several symmetry classes. So let me just very quickly go through some of these results. So we have formulas for many of the symmetry classes, as well as some other type of alternating sign matrices. And in some cases, the results are in terms of generating functions, not the exact formulas like the previous slide. So ignore the color for this slide. So what about a vertically and horizontally symmetric alternating sign matrix? Oops, sorry. So since this is a vertically symmetric, so you have that the middle column will be 1 minus 1, 1 minus 1, and so on. And again, there cannot be any ones except the middle entry here in the first row and the last row. Because it is vertically symmetric, this particular condition that the middle column was 1 minus 1 and so on would now be that the middle row will be 1 minus 1, 1 minus 1, and so on. So it will alternate between 1 and minus 1. Because this matrix, I'm also imposing the horizontal symmetry in this matrix. So again, it is not meaningful to ask this question that how many vertically and horizontally symmetric ASMs exist where you fix the first row or the first column, because this is always fixed in the middle, the non-zero entry. But you can ask a similar question that how many vertically and horizontally symmetric alternating sign matrix exist where the positions of the one in the second row you fix. Suppose here you can see that in the second row you have the one in the fourth column. So you can ask how many such matrices occur where the one is fixed in the fourth column or so on. And in this case, we have a generating function for this. So these are the numbers, these are the numbers that we are interested in. AVH would be the number of vertically and horizontally symmetric alternating sign matrices of order 4n plus 3, where the position is now fixed in the ith position. So here I have I plus 1. So what I'm interested in are these particular quantities in the right hand side. And if you so there is a start condition basically, because if you fix I to be 1, then this is 0, because we know that there cannot be a 1 in this position because of the horizontal symmetry. So I have a starting condition actually, so this makes sense. And whatever appears on the left hand side, I know this explicitly. So for example, this quantity AVC was now the quantity that I showed you 2 or 3 slides back, which was the number of vertically symmetric alternating sign matrix where you fix the position of the one in the first column. So this quantity is already known to us. And this Q and I is explicitly known. So there is a formula for Q and I. You can write Q and I in terms of some Lorentz styling of weighted Lorentz styling of some particular quartered hexagons. But I'll not go into this. But this quantity is known to us. And the Q here is now a sixth root of unity. And if you do this, if you expand this properly, then you will see that this Q will disappear, and you can just compare coefficients between two sides. So a similar result also holds for order 4n plus 1. So why this difference between 4n plus 3 and 4n plus 1? Because because of the difference between the statistical physics model of the vertically symmetric alternating sign matrices for orders 4n plus 3 and 4n plus 1. So if there is time, I'll show you, but just to basically maybe like an explanation would be that since our proofs are not combinatorial, so we have a bijection between these objects to some other object, and that bijection is between order 4n plus 3 and 4n plus 1. It's slightly different, so there is a minor difference. So these are the values. I already showed you this, which was the formula of Razumov and Stroganov. And the Q and I, which I said that is explicitly known, is something like this. So these are rising factorials in inside the braces. So also this is a rising factorial. Anyway, so the point is that we know explicitly what Q and I and AVC are, and this allows us to find out the refined enumeration numbers for the vertically and horizontally symmetric alternating sign matrix. So there is another class of vertical and horizontal symmetry alternating sign matrix, and this is called a vertically and horizontally perverse alternating sign matrix. So you see that this is no longer a square matrix now. If you count, I think the number of columns is 13 and the number of rows is 11. So this is no longer a square matrix, and there is a special entry in the middle. So the definition is the following for this special class of matrix is that all of the rows and columns except the middle row and the middle column satisfy the alternating sign matrix condition. That means entries are 1, 0, and minus 1, and the row and column sums equal to 1, and the non-zero entries they alternate in sign. So except the middle column and the middle row. For the middle column, again the entries can be 1 and minus 1 here. There cannot be a 0 because I'm imposing the vertically symmetric condition. There is a special entry which I denote by star. So what this means is that if you look from the top of a column, this star has to be read as a 1. So that means if you look from the top, you read this as a 1. But if you read this from the left to right or from right to left, you have to read this star as a minus 1. So if you read from this way, then this star becomes a minus 1. And if you read from the top, this is a 1. So this is called a vertically and horizontally perverse ASM. So we have the vertical symmetric condition, we have the horizontal symmetric condition, we have the alternating sign matrix condition for all the entries, except this particular special entry, which will be a 1 if read from the top, a minus 1 if read from the left. So since this is vertically and horizontally symmetric, again the question that how many of these particular exist if you fix the first row or the first column, it makes no sense because we already fixed the 1 in the middle. But we can ask a similar question for the second row. So how many exist where the position of the 1 is fixed in this particular second row? And since the number of rows and number of columns are different, you could ask the same question for the row for the second column now. That how many vertically and horizontally perverse ASM occur where you fix the position of the 1 in the second column. And we have formulas for both of them. So these are easier than the last generating function that I showed you. So by order 4n plus 2, I just take, so if the number of columns is 4n plus 3 and the number of rows is 4n plus 1, then I say that this whole matrix is of order 4n plus 2. Anyway, so there is a simple formula which is now sum. It's a sum over the quantities that were found by Razumov and Stroganov. So these are basically the refined enumeration quantities for the vertically symmetric ASM, where the refinement is in terms of columns now. So we can have simple relations between these two numbers. So if the row refinement is denoted by this, and the column refinement is denoted by this, then the row refinement can be written in terms of the column refinement. So this is immediate from the last two formulas that I showed you in the slide. So let's look at something called off diagonally and off anti-diagonally symmetric ASM. So this is the same matrix like before. So for off diagonally and off anti-diagonally symmetric matrix, we have the condition that the matrix is symmetric with respect to. So let me just read this. Maybe it will be easy to see in text. So what I have is that these matrices are symmetric with respect to reflection along the diagonal and anti-diagonal. And by the anti-diagonal, I mean, so this will be the diagonal, and by the anti-diagonal, I mean the opposite diagonal. Okay? And by off diagonally and off anti-diagonally, I mean that all of the entries in the diagonal and off diagonal are zeros, except the middle entry. So here, the middle entry is 1, but if you look at the diagonal, all of these are 0. All of these are 0. And then if you look at the anti-diagonal, all of these are 0. And the middle entry would be -1 to the power n, where n is now, where 2n plus 1 is now the order of this matrix. So for example, here the order is 9, so that means n is 4, so -1 to the power 4 would be 1. So the middle entry is 1. So again, you can ask a question, similar question. Since here I am not imposing the vertical condition, I mean, this is a vertically symmetric ASM, but I don't care about the vertical symmetry. I just care about the off diagonal and off anti-diagonal symmetry in this case. So we can have similar question, similar refined enumeration question for the off diagonal and off anti-diagonal symmetry case, that how many exist for a particular fixed row and so on. And we have a result which is similar to the vertically and horizontally symmetric ASM case. So from this result, there is a very nice relationship that we get, is that the vertical and horizontal symmetry refinement can be written in terms of the off diagonal refinement. So where this is a sum over 2, sum of 2 off diagonal refinement quantities. So, it is same for both the case, for order 4n plus 1 as well as 4n plus 3. And again, the proofs are not combinatorial, so I mean, combinatorial proofs would be welcome for this. So this should also remind one of the vertical symmetry case, where again the vertical symmetry case was written in terms of 2 other quantities, which were the column refinement. Okay.
Sorry, so what is the refinement here with respect to for OO?
This is first row.
First, okay.
Yes. So let me just quickly mention for the quarter turn symmetry case. So for the quarter turn symmetry case, which is a 90-degree rotation, which are ASMs which are invariant under a 90-degree rotation, we have again some sort of generating function formula. So these are the refinements that we're interested in. So a quarter turn symmetric alternating sign matrix cannot exist for order 4n plus 2. This is not very difficult to see. But yeah, maybe I'll just keep it. So it's not very difficult to see. So we can only have order 4n plus 1, and 4n plus 3. And all of these, we have some sort of generating function results for this. So you see that these quantities which appear on the right are now known. So A and I have already shown you multiple times. So this is now the refinement of unrestricted ASM. So AHT are refinement of half-turn symmetric ASM. I mean, it's not important what they mean combinatorially, but it is important that we know that these quantities, we have some explicit formulas for these quantities. For example, AHT2ni looks something like this, and you can also see that I have AHT2n plus 1i. There is a similar formula for 2n plus 1i. Okay. So let me skip this quasi-quarter turn, just show you the results. So there is again a similar result which holds for something called quasi-quarter turn symmetric ASM. Quarter turn symmetric ASMs are not, they don't exist for order 4n plus 2. So for 4n plus 2 order, something called quasi-quarter turn symmetric matrices exist. And there is a similar refined formula for this. So let me Yeah, let me just mention one of the new results, which is a bit complicated, so I did not write the full statement, but the essence is the following. So alternating sign matrices that are invariant under 180-degree rotation are called half-turn symmetric ASMs. And they exist for both odd and even order. And the refined enumeration for this with respect to the position of the one in the first row was already done by Razumov and Stroganov. And the formulas I showed you 2 or 3 slides back. So one could also ask for doubly refined enumeration. So remember that I mentioned that for alternating sign matrix, for example, for an unrestricted alternating sign matrix, you can ask something called multiply refined enumeration question. So which would be something like this. So you fix the position of the one in the first row as well as the position of the one in any of the other rows and columns, other boundary rows and columns. And if you do this, then if you fix 2 of them, then you say that this is a doubly refined enumeration. If you fix 3, then it is a triply refined enumeration, and so on. So for all of these 4 fixed enumeration, for example, if you fixed all the 4 boundary rows and columns of an ASM, there are formulas for these refinement. So one of them is by Arvind and Dan Romick, and one of them is by Roger Barron. So Roger's formula, I think, also considers 2 more statistics, but I'll not go into this. So one can do this. So one can ask for more than 1 refinement, and this is possible. This is not possible for all the symmetry classes. For example, for quaterton symmetric ASM, it is not possible. But one could do this for half-turn symmetric ASM, where you fix the first row and the first column, and then ask what is the number of half-turn symmetric ASM with respect to this fixed first row and first column. And there is a generating function formula for this, so where the quantities are explicitly known. So this is similar to the one that I showed for the vertical and horizontally symmetric ASM case. So if we go back just to show how this would look like, for example, here, so the formula would be something, you have a generating function here, and then you write this generating function in terms of products of 2 more generating functions, where you know explicitly both of these generating functions. So it's something like this. Anyway, so let's go to something else. Towards the last part of the talk, I want to show a different kind of refined enumeration, so which is called the 1/n phenomenon of quaterton symmetric ASMs. So the first observation is the following. So the central entry of a quaterton symmetric ASM of order 4n plus 1 is always 1. So this is the central entry that I'm interested in. So how to find this? So what you do is the following. So since this is a quaterton symmetric alternating sign matrix, so whatever entries they appear here, this particular block, I'm sorry, the matrix was not written very well, so it would have been better if there would have been one more row explicitly written about this. Anyway, so you look at the entries in this first quadrant. The sum of all these entries would be the same as the sum of all the entries here and here and here, because of the quaterton symmetry condition. Again, all of the sum of the entries in this row up to this, not counting this star, up to here, so these 2n entries, the sum of all these entries would be the same as the sum of entries here, sum of entries here, and sum of entries here, because of the quaterton symmetry case. So that means the sum of all the entries in this quaterton symmetry matrix would be 4 times the sum of entries of this particular block, plus the middle entry here. So this is written here. So 4 times this particular block plus the middle entry. And since the sum of all entries in one row is 1, and there are 4n plus 1 rows, so that means the sum of all the entries of this matrix would be 4n plus 1. So here you have something which is divisible by 4, plus there is a star, and then this should be equal to something 4n plus 1. So the star has to be 1. The only possibility is that it is a 1. So that means the middle central entry of a quaterton symmetric ASM is 1. And you could do the same thing for order 4n plus 3, and you will see that the middle entry for such a matrix would be a minus 1. So because of the symmetry, all adjacent entries of this central entry are the same. So this entry is the same as the one above, the one below, and the one to the right because of the symmetry, quaternion symmetry. Okay. So the proportion of quaternion symmetric ASMs of appropriate order with fixed entries adjacent to the central entry was conjectured by Stroganov to be n plus 1 divided by n. So that means, see here, the central entry is a 1. So the only possibility for this entry, which is adjacent to the central entry, is a 0 or a minus 1. So it cannot be a 1 because of the alternating sign condition. So what Stroganov conjectured was that the proportion of entries where it is 0 to the proportion of entries where it is minus 1 is n plus 1 divided by n. Okay. And this was already observed for quasi-quaternion symmetric ASMs by Aval and Duchon, and for the case of half-turn symmetric ASMs by Razumov and Stroganov, and also for odd-order diagonally and anti-diagonally symmetric ASMs by Baron, Fischer, and Konvalinka. So this phenomenon is known for several of these classes. For some reason, this quaternion symmetric case was not looked at by anybody. And we proved these two conjectures of Stroganov recently. So which is the following. So the number of quaternion symmetric ASMs of order n with entries adjacent to the central entry, with the entry adjacent to the central entry being something like this. So if the central entry is 0, then I replace the star by 0, and if it is 1, I replace it by 1. If the adjacent entry to the central entry is 0, I replace the star by 0. And if it is minus 1, I replace it by minus 1. So for order 4n plus 1, since the central entry is 1, so I have this proportion, which is n plus 1 divided by n. And for order 4n plus 3, I have this proportion, which is 1 n divided by the 1 where 0 occurs. And again, the quantity is the same. And this brings me to the end of the talk. So these were the things that I discussed. So we proved singly refined enumeration for almost all symmetric classes. Some of them I did not show, and this proved some conjectures. Then we proved some singly refined enumeration for related classes of ASMs, like off diagonally and off anti-diagonally symmetric ASM, which I showed. Something else also was done, which I did not show in this talk. And this actually, all of these results, it completes the singly defined enumeration of ASM. So for the boundary statistics, we don't have any more refinements to be done. And we also proved a doubly refined enumeration for half-turn symmetric case, but there exist other doubly refined enumeration cases which are not yet done. For instance, for vertically symmetric alternating sign matrix, one could ask similar question that what happens if you fix the second row and the last but one row, and then ask a doubly refined enumeration for this, and so on. And we also showed you some conjectures of Stroganov about this 1 over n phenomenon of quaternion symmetric ASMs. So this was what I wanted to mention, and thank you so much for your attention. So I have some proof techniques. If anybody wants to see, then I can show you one or two. Thank you.
SBM had a comment. Do you want
Yes.
to ask that?
Yes. Oops, sorry.
Okay, I'll ask on her behalf. So she's saying, Manjil, just for information, the matrices involved are also known as stochastic matrices, and I used to study majorization problems.
Okay.
No, that's false. I already responded to it. These are not stochastic matrices because they have negative off-diagonal entries. That's not. It's not possible.
Okay.
There's stochastic or bistochastic have to have non-negative and positive entries, So that way, only stochastic properties that the sum is 1 for rows or for columns, and by there's a nice article by Sundar, which is accessible to undergraduates also on bistochastic matrices, and that is the convex hull of permutation matrix. Okay. Now, Manjil, how do
Yes.
you identify permutation matrices amongst your ASM matrices? Is there a way to characterize them?
Yeah, so this is so no, not really. In my setting, no, I don't care about permutation matrices. But for example, I mentioned that there are these missing bijections between alternating sign matrices and other classes. So one of these should be something like you should be able to get the permutation matrices separately out of this bijection, and this was done actually by Irwin for descending plane partition. So he has a bijection between descending plane partitions, special class of descending plane partitions and permutation matrices. And I
And
think also Jessica Strider has different.
what
Sorry.
happens to the midpoints or products?
So midpoints of what?
Midpoints of two ASM matrices. Will
Um,
that be, when will that be ASM, or products of two ASM matrices?
yeah. I think products of ASM matrices are almost always not ASMs. For midpoint, I don't understand the question. So you mean that if I have an alternating
A
sign
plus
matrix and
B by
I
2. A and B are ASM. When is A plus B by 2 an ASM?
okay. Well, yeah. So I don't know when it is, but it's easy to see that for most of them it won't be
Yes.
because yeah,
So I just wonder,
because the some condition would be violated for many of them.
uh-huh. The stochastic property is satisfied for both. Sum is one, or in 1 1 1 1 is a fixed point. Stochastic condition for rho, it can be put down, that image of one is one, and for image of transpose of image under transpose of 1 1 1 is one. That will be
Mhm.
the column wise stochastic property.
Okay.
But whether there are any or not, I don't know.
Manjil, I have a quick question.
Yes.
So, for vertically symmetric ASMs, do you have doubly refined with respect to row and column, second row and first column?
No, I don't have.
Is it something you looked at, or it's
Yes, so I was looking at it, not very recently, but I was looking at it, and there were some problems in the approach that I was trying. Mainly this division by zero business, so there was some problem with that.
oh, okay.
But it is something which I was looking at before. Yes.
Yeah. Okay,
Uh,
thanks. Nice talk. I have to leave now, but thanks. Yeah.
Thank you.
left multipliers or right multipliers.
Sorry, can you repeat once again, Professor Singh?
ASM into ASM, or
What
your
is a
classes.
so you are asking what is ASM into ASM?
No. I'm asking, take the set of ASM matrices or your special ASM matrices. Which
Mhm.
matrices, when multiplying such matrices, give you back ASM matrices, the same type matrices? They are called multipliers.
Okay. So I would not be able to answer this. I
So
don't have.
left multipliers, what are left multipliers? What are right multipliers? Like
Yeah.
there is a result of synchron that matrices can be turned into bistochastic matrices via some diagonal matrices.
Mhm.
And the synchron is in Wikipedia, so you can
Okay.
just see synchron's results.
Okay.
So
Thank.
that is why I am asking which, and also I work on multipliers. So that is why I'm asking which matrices are multipliers, left or right or both sided or what.
Okay. So I would not be able to answer this question. I don't know.
Okay. So, any other questions or queries or comments to Manjil? Okay, then thank you, Manjil, for a really nice talk. Um, yeah,
Wonderful talking to you.
yeah,
Thank you.
good talk. I am. You, you can say
Thank you.
Thank you.
Very nice.
So what happens now?
Let's just say hello. Whoever wants to say hello. I should just stop recording.
Not completely.